Good day, ladies and gentlemen. Today we're going to talk a little bit about chemical change. Now, this module or this section of work is one where people tend to get confused quite often. So I would advise that you make a little sheet with all of your abbreviations, your constants, and your formulas on to sort of help you work through this. You will also need a periodic table at some point during this section of work. Not in today's video, probably, but we'll see how fast we go. This is the periodic table I use. Those of you who are in my personal science class, I will have given you exactly the same one. Those of you who are not in my class, you can find a periodic table without any difficulty whatsoever on the internet. Just make sure that you actually have a nice one that gives you the atomic number, the atomic weight, the important things. Now, for this section of work, we are going to have two constants to work with right now. The first constant that we have is Avogadro's constant. Avogadro's number. We abbreviate that as Na, and that is equal to 6.02 times 10 to the power 23 mole. We then also have the molar volume of gas. Molar volume of gas, and that is equal to 22.4 per mole. Now, when we are talking about chemical change, the first thing that you need to bear in mind is the concept of stoichiometry, which is an unpleasant word to spell, which I'm sure I've also spelled incorrectly there. But this refers to the branch of chemistry that involves the ratios of atoms, molecules, and the formulas of those. So if you were to use a ridiculously simple example, we could say H2O, water. It has 2 hydrogens and 1 oxygen. So its ratio would be 2 to 1 for hydrogen to oxygen. It's a very, very simple example, but it's just to illustrate that we're talking about ratios. You then also have the relative molecular mass, or the relative formula mass. Now, these two terms are very often used interchangeably, and what these refer to is the sum of the atomic masses of all of the atoms in a formula. Now, if I get back to my periodic table, you will see the atomic weight. Now, every atom has a weight, it has a mass. This relative molecular mass refers to the mass of everything in the molecule, all of the atoms' mass together. So for something like water, continuing our example, it would be the mass of the hydrogen times 2, because we have 2 of them, plus the mass of the oxygen times 1, because we only have 1 of them. So it takes into account the masses of all the different atoms in your molecule, as well as obviously then the amount of those atoms. And you can, using that, calculate the actual mass of said atom. Now, this is where things get a little bit more complicated, because we now have something called mole. Now, a mole is the amount of a substance, let's write that there, mole, is the amount of a substance that contains the same number of elementary units, that is to say atoms, as the number of atoms in exactly 12 grams of carbon-12. Now, we use carbon as sort of our standard for most of the things that we do in chemistry. So, in short, you would say 1 mole of whatever we are looking at contains 6 to the 0.2 to the power 23 particles. So if we say I have 1 mole of marbles, that means I have 6.02 times 10 to the power 23 marbles. That's a hell of a lot of marbles. Okay, so this is also called Avogadro's number, 1 mole. So you need to know this number. You need to know what 1 mole is. So if I tell you I have 1 mole of lithium, that means I have that many lithium atoms. This is very, very important. Now, we continue on and we say 1 mole of a substance has a mass equal to its relative formula masses in grams. 1 mole of a substance contains 6.02 times 10 to the power 23 atoms, molecules, or formula units. And now we get something called a molar mass. The molar mass is the mass of 1 mole. So I would say that the molar mass of carbon would be 12 grams, because 6.02 times 10 to the power 23 carbon atoms, 1 mole of carbon atoms, weighs 12 grams. 1 mole of water weighs 18 grams, because 6.02 times 10 to the power 23 water molecules weigh 18 grams. Now, this does sort of give you a bit of an idea of exactly how tiny atoms are, because this number, 602, if I counted correctly, that's how many atoms we are talking about. And 18 grams, that's not a lot. So it does give you an idea of how terribly tiny atoms and molecules are, and also of how huge this number is. Now, of course, we need to be able to calculate this, because where's the fun if we don't do that? So, we have a very simple formula, and despite being such a simple formula, people tend to make mistakes because they do not use the formula correctly. We start number of moles. That is the amount of moles. 2 moles, 3 moles, 5 moles, 0.2 moles, how many ever units. Remember, a mole is a unit, like a dozen. So we can say I have half a dozen, I have half a mole. The number of moles is equal to the mass, that 12 grams of carbon or 18 grams of water, divided by the molar mass. If we abbreviate this, this gives us lowercase n is equal to lowercase m over capital M. And I realize now that my capital M looks exactly the same as my lowercase m. So I will endeavor to perhaps try to write a little bit more thoroughly, but yeah. Now, mass, the lowercase m, that is grams. That is always grams. No matter what unit you get, you convert that to grams. The molar mass, that feels very weird to write an M like that, but okay. That is going to be grams per mole. So if we are talking about water, for instance, I have 27 grams of water, and the molar mass of water, 1 mole of water, is 18 grams. So how many moles of water molecules do I have? And then, of course, N is your number of moles. That is perhaps a very nice little example to do. The mass of water that we have, let's say 27 grams. The molar mass of water is about 18 grams. Now, the question then is, that will be mole, how many moles of water do I have? So, N is equal to M over M, 27 over 18, and if I can find my trusty calculator, then 27 divided by 18 gives us 1.5 mole. And that actually makes a little bit of sense if you think about it, because 1 mole of water weighs 18 grams. We have 27 grams of water. That means we have 9 grams of water left, which is half of what 1 mole weighs. So in 27 grams of water, we have 1.5 mole of water molecules. Now, this is a very simple little example, but this is the kind of calculations that you can expect. Although sometimes you would not get the mass or the molecular mass, and they would give you the mole instead. It's still going to be an equation where you only have one unknown, but they try to make it a little bit tricky. Now, I would highly recommend that anyone who has a textbook, please look at some activities for this. Okay, those of you who are in my physics class, again, I have the same textbook as you, so I can recommend some activities for you if you're interested. But any textbook that's actually sort of worth its salt should give some nice examples on this. This is something that you actually sit with pretty much the whole time. It doesn't go away. I did this up to my first year in chemistry. Now, that is just the basic, easiest bit of calculating these masses. Now, it gets a little bit more complex from there. So let's make that little page we said, and we have N is equal to M over N. That's our first formula. Now, we also have something called a concentration and the molar volume and all of these things. And to sort of abbreviate these things as shortly as possible, we can say the concentration of something that you mix can be calculated as C, lowercase c being the abbreviation for concentration, is equal to mole, which we know is a lowercase n, over volume, capital V. Let me just write concentration, and here we have mole, and I think I will just here at the bottom say N is equal to mole, M is equal to mass, capital M is molar mass, C is equal to concentration, and V then volume. So what this in essence tells us is that if we have a certain volume, let's say 1 liter of water, and we add 1 mole of whatever we are mixing into it, that gives us a concentration of, well, in this instance, 1 divided by 1, so 1. If we then were to take, again, 1 liter, but now add 2 moles of whatever substance we were adding, 2 divided by 1 is 2. So our concentration is 2. So that tells us that whatever it is that we have mixed into that water, the concentration is higher. Now, of course, you can increase the concentration by either increasing the moles, the amount of stuff you add, or by decreasing the volume. Now, we can, of course, swap this formula around a little bit and say that the moles that we have is equal to the concentration divided by the volume. Or we can say that the volume is equal to the moles divided by the concentration. It's just switching the formula around a little bit. You can do exactly the same thing with the first formula we had. Now, of course, this is still a little bit too easy. So what we do is we combine them because, well, frankly, because we can. So if we have these formulas and we then add our mole equation in there, then we can say that concentration is equal to the mass divided by the molar mass multiplied by the volume. Or we can say that the mass is equal to the concentration times the volume times the molar mass. So we start getting our formulas being a little bit more complicated. And these are actually kind of important because I can supposedly give you a calculation and I can tell you that I have a concentration of sugar water and the volume is 1 liter, the concentration is 1.5 and the molar mass of sugar is 17, whatever. Calculate the mass of sugar I added. It's just a little example, but point is you can get some very interesting and arguably pretty complicated calculations out of this. I say complicated because they seem terribly complicated, but if you just, in essence, have this in front of you, your little cheat sheet, if you will, your formula, and you know what each of these things are, and you just take the information out of the question, it actually becomes not that difficult. It then actually becomes very simple, almost marks for free. Now, I also realize that some people just struggle with this stuff. We all have our aptitudes, we all have our strengths and weaknesses. I remember when I was in high school, this was something I just couldn't quite wrap my head around it. It was only in university when I sort of really snapped. So if you are struggling with this, if you would like another video on something very specific or some examples worked out maybe, let me know. I'll see if I can make a plan. But if you just have this, you should be fine. Now, the final thing that I want to talk about in this video is the idea of neutralization reactions. Now, a neutralization reaction is what happens... Oh my, I still can't spell. I'm just going to progressively write uglier and uglier until no one can write what I say anymore, and then they can't say that I spell everything incorrectly. Neutralization reactions, these refer to a reaction between an acid and a base. or an alkali. Now, you might be wondering what this has to do with what we've spoken about with concentrations and voles and volumes and everything. And the answer is actually, if you think about it, sort of intuitive, because acids and bases cancel each other out. You might have heard, if you spill an acid on yourself, don't wash it off with water. Chuck a base on it, because the acid and the base will neutralize each other. This is exactly what we are doing. If I have 17 moles of acid, how many moles of base do I need to neutralize it? And now you might say, oh, well, 17 moles of base, so 17 moles of acid. But what if I don't ask you base or the base's volume, I ask you its concentration or its mass? That's where the formulas come in. So, in essence, what we have is, I'm not going to go through all of the theory for this. I'm just going to do this very briefly as a section of what we've done now. If you want something more specific on this, let me know and I'll make a video. More or less what happens is, we calculate an unknown concentration for a balanced chemical equation for something where we know the concentrations. Now we know that concentration is equal to the moles over the volume. Now this is called titration. If I know for a fact the concentration of chemical 1, I know its volume, its moles, its concentration, everything perfect. And I have another chemical, chemical 2. I know how much volume there is, but I mean I've got it in a beaker so I can measure it. I don't know what the moles or the concentration is. Then we start mixing them. Because what happens is, the moles of A over the moles of B is equal to the concentration times volume of A over the concentration times volume of B. So if I tell you that I have a chemical, I know its moles, concentration, volume, everything, and I have a second chemical, I know its concentration and I know its volume, but I don't know how many moles of whatever that substance is has been dissolved in it. I can now use this formula to calculate that. And we do that with acids and bases sometimes, and also in what we call titration reactions, determine the concentration of an acid or of a base. And we do that by, obviously, we know how many moles and the volume of the acid, but not the concentration, so we add a base for which we know everything. And using this formula, we then only have one unknown, we get the concentration. Now, in my personal, humble opinion, these and understanding this is more important than understanding this. That is my personal opinion. I obviously cannot say what will be in exams and such, but that's my opinion. If I had to say the thing I've seen being asked the most frequently was based on this. So I would start here. Now, moving forward, there are some stoichiometric calculations that we can do, and we can obviously then apply these formulas in practice, and I will do those in a next video, and that should actually then be the end of this. In theory, there are a few other things like limiting reagents and such, but for the most part that will then be the end. Now, I do not personally believe that the section of work remaining, the actual calculations, are that challenging. If you have all of this done, dusted, you understand, you're fine. So I'm not going to have making that video be at the top of my priority list. If you guys have watched this video, try doing some calculations out of your textbook. If you struggle and you need help, specifically with this, with calculations, let me know and I'll make a video doing a few calculations for you guys. That's it for today. Until next time, ladies and gentlemen, have a nice day.